Hello, Algebra 1B. So we are going into section 11.1B, and as we go into section 11.1B, we do have one thing that should look kind of familiar to us on this board or on this screen. That one thing being this X bar guy, and this X bar guy, maybe remember, is the mean, not the median, middle, not the mode, most, but the mean. He's that arithmetic average guy, that one that you've learned for a long time, adding up all the values, dividing by how many there are. That's what teachers do or programs do when we tell you what the average score is on a test or something like that, or the average height of kids in your class, or there are all sorts of things that we can average, anything that has numerical data. But this guy is technically reviewed, this little X bar guy, but what is going on with this table? To figure that out, we need to dive into section 11.1b and see what else there is for us to learn. So the nice thing is our terms today do start with something that you guys saw yesterday, outlier. If I was to read from the book itself, if I can get this to zoom in, it's having some issues focusing today, and I'm not sure why. Let's see if we can shed some light on the matter and if that's going to help out at all. Let's try again. Letting it zoom. Are you going to find it? A little bit fuzzy. It works one second and it doesn't work the next. I think it might be because my hand's in there and so it's getting a little confused. Let's let it try to go back on the table. That is what we're supposed to be learning today. We can do real well when we do that, but as soon as we put an iPad, it gets a little confused. There we go. All right, outlier. Outlier is from the book, and it's a term that we saw yesterday. Much greater than or much less than. If I go in and out, it's just because sometimes I'm facing the speaker and sometimes I'm not. So turn your volume up. I can't totally fix that since I'm working on the whiteboard, but I can try to talk louder. Outlier, it is that data value, and that's a little bit thick. It is that data value that is far greater than, that's the point, far greater or less than basically all the others. Just, it's weird, it's out there, it is just so different. So we can say less than the other values. I'm just going to make it pretty general and pretty vague. So far greater than or far less than. And yesterday that example was of like that baby gorilla, where it's like all of them are these huge number of pounds, and this little guy, man, he's only 60. What's going on? Oh, it's a little one. It must be like a baby. They didn't say adult gorillas. So that was from yesterday, a term that we didn't get to write down, but we have three other ones that are going to be new to us today, with measure of variation, range, and standard deviation. We're getting kind of technical, actually. Parents, family, siblings might be pretty impressed if you mentioned to them that you learned today about standard deviation. That's just a very common word in statistics, but it doesn't mean it's not a little bit complicated. Have your calculator close, be ready to go. Let's finish off chapter 11.1 so that you guys can finish up that homework. Do remember, both of these videos watched, you don't even, I don't think, need to go to Google Classroom and mark as done. I think you just watch them all the way through from the link in Classroom. If they ask you for an email, use your Heritage Warriors. But watch the two videos, it'll automatically be done. It'll give you like 100% as soon as you've watched them. And then you need to go ahead and do 11.1A and 11.1B homeworks. Do that on just your homework spiral on separate paper. Take pictures and submit them by Friday night, midnight, okay? Then we have a puzzle time that's coming too, but we'll talk about that one later. So 3 terms for today. Measure of variation. Yesterday we saw a measure of center. We were trying to find that typical or that center value. But now measure of variation. Variation. If there's variation in flowers or variation in foods or variation in people, that means there's some varying degrees of or varying characteristics. Another way to say it is that there's some characteristic that varies amongst them. Doesn't variation, varies, varying, doesn't that kind of mean like changing? Measure of variation, how much change there is. Measure of variation. So measure of center yesterday, once again, with the typical was the center, was like the basic type of value. It was one single value, and maybe the mean, maybe the median, maybe the mode, maybe one of those was a good measure of that center. But measure of variation is instead the measure that describes the spread or the distribution. This one's talking about the spread, how spread out it is another way of thinking about it. the spread or the distribution, how distributed the values are. How spread out they are, how distributed they are. Is it distributed evenly amongst all these different values? Are they clustered or clumped together? Those are some different things that we could be seeing or hearing or thinking about. So there's two different terms for us to talk about. One is range and one is standard deviation. Range, this one's actually the easiest one mathematically to solve for, but it might not always be a good measure of variation. The range is basically, another way of saying that would be the difference between the lowest and highest value. You say, how spread out is it? You're like, oh, no big deal. What's the lowest you go? What's the highest you go? And subtract the two. Literally, remember, in math, difference literally just means subtraction. So the difference between the lowest and highest value. What's the lowest it goes? What's the highest it goes? Before we go to standard deviation, let's go ahead and go look at an example problem. I think I have the one that we're going to practice right down here with, here we go. The heights of members of two different girls' basketball teams. They're asking us to find the range of heights for each one. If we were to peek really quickly at the book before standard deviation, here we go, range. The difference between the greatest and the least is what they say. They give us, I believe, 2 reality cooking shows, 12 contestants and how old the contestants are. The range is literally taking each list of data and saying who is the oldest and who is the youngest. What's the greatest, what's the least, and just check it. 31 was the oldest, 19 was the youngest. Subtract the two, that's the range. There's 12 years in between the lowest and highest. So the range is 12 years of the first show. Second show, the range is 29 years. What does that tell us about the show? Well, maybe the first one is made for younger people, whereas the other one is made for older people. That might be as simple as the explanation goes. It might be a bit more complicated, but the ranges are just the lowest minus the highest. So if we were to go to our example, we would have to go ahead and look at team A heights and team B heights. One way to figure out the lowest and the highest would be to order them like we did yesterday, as far as, hey, the very first one that I see would be 48. That's the lowest or the shortest person on this team, 48. And then we would keep going and we would have, I believe, 54 is next, and then 56 and 57, 58, 59, 60. And then there's a bit of a gap, oh, 2 60s. Then there's 75 and then 78. So we have a little bit of clustering, I think, that happens right around the 60 areas. But long story short, our lowest, we were to try to identify our lowest, if that's what we need for range, lowest and highest. The lowest is going to be, I believe, this guy. Oh, nope, 48. 48 is going to be our low or our lowest. And as we look at the highest, I think it was 78, the tallest person. Lowest and highest, or least and greatest. You could put a G2. So you have lowest and highest. And so range literally just says, hey, take the highest minus the lowest. Now we can keep on looking at the other one. I think I see 49 as the lowest or the shortest. The highest being, oh, not quite so tall. This one is a bit more condensed. I think I see 70 as the highest. So I have the low and the high of the next one. So for team A, lowest minus highest would be 78 minus 48. For team B, lowest minus highest would be 70 minus 49. And so for team A, my range is going to end up being 30. And for team B, my range is going to end up being just 21. For team B, they're definitely closer to the same heights, whereas team A, they're more spread out. We can kind of see that. And that's one way of saying the spread, the distribution, the measure of variation, how varied they are. But that's not the only thing that we're going to talk about today. There is one other, that more complicated, but also, to be honest, more helpful term of standard deviation. Now, standard deviation is a little bit harder. We're not going to worry about this data transformation. You might see one in homework, just basically follow the directions. It's not something for you guys to stress about. We're going to stop with standard deviation, but let's go ahead and try to look at what the book has to say about standard deviation before we write down a definition of this guy. So the book, when I'm looking at standard deviation, here we go. It does look a bit complicated. Not as complicated as it sounds maybe, or as complicated as even it looks right now, but that is the reason why we have this big old table set up behind us, is to be able to actually find some standard deviations in just a second. So let's check out and see if we can understand what the book is saying. The standard deviation of a deviate, to deviate from something, to go off the course. The standard deviation of a numerical data set is a measure of how much a typical value in the data set differs from the mean. How much a typical value in the data set differs from, how far off, differentiate, deviate, varies, how far off it is. Anyway, so differs from the mean. Hey, the mean, isn't the mean that guy we were just talking about that we did yesterday? The mean is that X bar guy. And if you guys check out down here in this formula, I see X bar, wait, I see subtractions and I see squareds. Maybe that's where all these guys are coming from. Maybe we're building up to being able to use this formula. Now, one thing that you're going to need to see for what we're about to do is that there is this new Greek letter sigma that a lot of you guys haven't seen before. It's technically a lowercase sigma. Greek letters actually, yes, they're important for like sororities and naming frat houses and things like that. However, Greek letters are also used a lot in math and physics and science, like upper sciences. Yeah, those Greek letters do come back. So, or come back, they show up and they are used to talk about a lot of special things. And so this lowercase sigma guy, he's actually used in statistics to talk about standard deviation. So that's one thing we could write down as far as our term. There is this Greek letter that represents standard deviation. He does talk about how a typical, or how much a typical value differs from. I think we just kind of got our definition. So standard deviation, we can kind of put in parentheses. He's that little sigma guy. Think like a little zero sort of with like a little hat on, like a little bar on top. So we have that little zero with a little bar. So we have sigma being a Greek letter that represents standard deviation in statistics. But what is he? He represents how much a typical value differs from the, wait, what is it that he differs from? X bar or the mean. If you want, you can go ahead and remind yourself of what the mean is symbolized by, which is X bar. It's a messy X bar. Try to make a little bit nicer one. There we go. So we have all of our different terms defined, but we definitely have not solved for a standard deviation yet. So we're going to go ahead and go do that now. So standard deviation, let's go ahead and peek really quickly at what those steps are to fill into this formula. At the end of the day, thinking about PEMDAS as far as the order of operations, if that helps, we are going to say that that sigma, or that standard deviation, is equal to, this square root is actually the very, very, very last thing to happen in this formula. There's a lot of things going on underneath first. So if you guys notice, the square root is the very last step. Square root of, wait a minute, there's a new vocab word. Square root of the variance. Who's the variance? Well, guys, what is under the square root up here? Isn't everything under the square root? So standard deviation says find the square root of all of this, and all of this must be called variance. Oh man, well that's kind of messy. I'm going to go ahead and try to get my highlighter marks back in. They kind of took them all away. But variance is this big, huge, oh, we got to break it down. That's a mess. Okay, so let's keep going. So we need a square root of the variance. And then if you guys notice, who is the variance? Well, it's a big old division of lots of additions divided by n. Wait a minute, yesterday, who was the guy that said add all these different things up and divide by the number, n, the number? You guys check out right above, the mean is who's underneath that square root. So the variance is the mean of who or what? The mean, or the mean of, I should say, of the squared deviations. Well, squared, okay, that's pretty obvious. I see squared because there are squareds everywhere, but what's this other term, deviations? What's this other term, deviations? Who or what is being squared up here? You guys see those subtractions? Deviations are the who or the what that are being squared, and that's those subtractions of, well, wait a minute, who are those subtractions? Okay, if we go up one step in this step, it says squared, and it's like, okay, duh, I get it, squared means squared. We just talked about how deviation is this subtracted dude. Okay, fine, deviation, the subtracted dude. But then, well, who's X? I think it might be best if we right now look at an example to try to figure out, wait a minute, what are we putting in here? And how are we actually doing all this math that leads us to this final guy of the standard deviation, which once again is talking about the typical, or I should say how much the data differs from the mean. How much the typical data differs from the mean. Okay, an example. Let's look at one totally solved now, and then let's go ahead and go try to do it ourselves. So standard deviation. Step one, find the mean. If they don't give it to us, we have to go find the mean by doing what we did yesterday, which the mean, remember, the mean yesterday was go ahead and, let's see if I can get let's get a red marker. The mean was kind of what we saw yesterday. I know it's purple, it's close. The mean says, remember, add up all the data, divide by the number. So there must have been 12 of them. Adding them all up must have gotten 300. So then we had the mean of 25. But whenever you see the X bar, you are supposed to, in this formula, replace the X bar with 25, which maybe you guys can do some mental math and see. Now hold on, what does step number 2 say? Step number 2 says you need to find the deviation of each data value. Well, okay, data value. That must be talking about this X guy because I know who X bar is, and X bar is that mean guy that we already found from up above. No, not the angry one, the average one that we found from up above. We're going to take each data value and subtract the mean. Then we're going to do this squaring step, wrong color. We're going to do this squaring step, taking each of those deviations and squaring them. Then we're going to go ahead and find the mean of those squared deviations, or that's what that snazzy word variance is. So we're going to add up all those squares, divide by the number of how many we have. Then we're going to go ahead and finally take the square root of that guy called the variance and be done. So let's go ahead and go get our own examples so that we can actually practice this without staring at what someone else has done. So coming on back down to our girls basketball teams, we have already figured out the ranges of those girls basketball teams, the heights. What the highest is minus the lowest. We've already found that. Now it's time for us to find the standard deviation of A first, and then depending on time, we might go ahead and go to B also. But I'm going to go ahead and use my whiteboard right below for this. So if you guys want, you could take just a second to pause the video and take a picture of these tables because I'm going to be using these tables as we fill in down below the different data points. Now to be all nice and organized, I'm going to go ahead and just go in the order that it's written, but you could also go in the order from lowest to highest. That is not inappropriate by any means. But I'm going to go ahead and take each and every one of these team heights. I'm going to, ready? Fill it into the X column. So the mean is the X bar from yesterday. We just saw that this guy is called the deviation. That's what this subtraction is called, is the deviation. This one is literally just, the book tends to call it the squares of the deviation. Oh, let me zoom out just a little bit. The squares of the deviation. And then this one, here we go, are going to be our data values, aka those are the beginning values that were given. So in this one, looking at the table that I hope you guys took a picture of, we had the following data values. And I'm going to go ahead, and I think I had that team A being blue, which I did. That started with 58. Then we had 75, we had 60, we have 48, 56, 78. Uh-oh, a lot of girls on this team. 60, 57, 54, and 59. Whew, barely got it. I think I might have to zoom out just a little bit or move my whiteboard up just a little bit. There we go. 59 was our very last one. Let me just extend my table just a little bit. So there we go. We have all those different heights of the girls basketball team. Now, the problem is for the very next column, we need to find the mean. And the mean is that review guide that we talked about just a little bit ago. So that mean, I'm going to go ahead and turn my calculator on as well. Let's come back and ask ourselves the question, what is X bar? Well, X bar is, remember, the sum, adding them all up, the sum of however many data points you have or data values divided by the number of values. Oh, let's write that next to each other. The number of values, how many there are. So maybe you guys can be going ahead and counting up how many values there are. I'm going to go ahead and in my calculator start putting all of these in. 58 plus 75 plus 60 plus 48 plus 56, making sure I'm typing them in right or else everything's going to be off. Then I have plus 78 plus 60 plus 57 plus 54 plus 59. As I was doing each of those, you guys should have been counting up for me 1, 2, 3, 4, 5, 6, 7, 8, 9. Did you figure out that there were 10 different values? In this problem, when I add up all of them, I get 605, and I need to divide by those 10 values. So if I divide by 10, I end up with a mean of 60.5. Now, the book tends to go ahead and rewrite this mean over and over again. I'm not exactly sure you need to, but for all of these data points, this entire table has the exact same mean, the exact same arithmetic average. So I understand why they're writing it down. I think it might be a little tedious, but the reason why they're writing it down is because now what we need to do for every single one of these is check out the next column, subtract the 2. What is this data point minus its mean? And so if I take 58 and I subtract the 60.5, I'm going to end up with negative 2.5. If I do 75 minus 60.5, I'm going to end up with, well, is that going to be 15.5 or 14.5? 14.5. We can almost do that one in our head. Some of us might have been able to. 60 minus 60.5, oh man, that's close. That's 0.5, but a negative. 48 minus 60.5 is going to end up being negative 12.5. 56 minus 60.5 is negative 4.5. 78 minus 60.5 is going to be 17.5. I'm going to have a negative, another negative 0.5. Then I'm going to have a negative 3.5, a negative 6.5, and then a negative 1.5. If you guys want, we could go ahead and double check that I'm doing this right. Minus 60.5, got him. So a lot of number crunching, hence why you're having your calculator close, your little one or your big one, doesn't matter. But now we have to go on to the next step. And the next step is now it's time to, ready, read the words. Square each of these. So I'm going to go ahead and take each of these values and square them, which I know once again is a little bit tedious, but statistics is a lot of number crunching. Now be careful. Remember when you square a negative number, a negative times a negative is a positive. So you could type in a negative 2.5, but you have to put them in parentheses so that when you square it, you get a positive number. Another way of doing this is realizing every negative squares to be a positive. Every single one of these, since it's being squared, should be a positive. So I can just do something like 2.5 squared and 14.5 squared, 0.5 squared. Ooh, I'm going to be able to use 0.5 squared for another one because that was a repeated one, right? There we go. I'm finding each of my little squares, typing in everybody. I'm going to come back and grab them all in just a second. I have 17.5 squared. 0.5, I already did that one, so I'm not going to do that one over again. 3.5 squared, 6.5 squared, and 1.5 squared. I'm going to go ahead and go backwards filling these in. But I get my, let's put them over here, my 2.25, my 42.25, my 12.25, a lot of 0.25s, huh? To go find that 0 guy. Who is that 0 guy? I get to put him twice. That's, oh, 5 and 5 is 25. Maybe I should have been able to figure that one out on my own, huh? And then if I keep on going, let's see, it's time for that 17 guy who's a big number, which is 306.25. I just did all these in my calculator. To 10.25 and 6.25. Those are a lot of numbers. Those are definitely a lot of numbers. Good thing is I think I only gave you maybe two of these for homework where you actually have to find the standard deviation. And you're like, man, whew, all right, we're done. But hold on. Remember, in standard deviation, we have this whole formula. What we've done so far is we've found the mean. Check. That's actually one of the first things that we did, which was 605 divided by 10, adding up all our data, dividing by how many there were. That's how I got 60.5. So we found our mean. Check. We went ahead and found the deviation of each data value. What's the difference? Subtracting each of these, we found all our deviations. Then we, next step, squared all our deviations. Man, we're all the way down here in our final step of find the mean of those squared deviations and then square root. So to find that, let's see what's underneath. Aha. To find the last two steps. Standard deviation. He's the guy that says, I'm going to take the square root of the variance. So to find me, use square root, but the problem is, in order to square root, I have to find what the variance is. So let's go up and see, okay, the variance. The variance, according to our notes, is, we can check it, the mean of the squared deviations, the mean. Now check it. Isn't the mean telling us to, I need to get my calculator because I'm going to have to use it in just a second. Isn't the mean telling us, the arithmetic mean telling us to add them all up and divide by how many there are? We know that there are 10 different data points. So right now I have 10 different squares of deviation. But I need to go ahead and find the mean. Well, to find the mean of the squares, I need to add all of these. Now, I'm not even going to write it out. I'm just going to put it in my calculator and do it. But I need to add all of those together. So if you guys want to check my work, I'm going to go ahead and put in 6.25 plus. You guys can imagine some people that have to put in lots of numbers must get really, really good at typing numbers fast and typing them accurately, because if they make a mistake in the numbers that they have to input, that could be a rough thing. Now, it is true that there are computers these days that might be able to do some of that typing for us. Well, it doesn't mean that they're necessarily taking all of the data analysis jobs, because data analysis requires some creativity sometimes. 2.25, 42.25, making sure I have them all. 12.25 came next, 0.25 was before that, 306.25 was before that, 20.25, I got it. 156.25, got them. I have 0.25 before that. I have 210.25 before that. Whew. All right, I've added all of those together, and I think I've done it in an accurate way. I have 756.5. So now all I have to do is do that 756.5, divide by 10 to get my variance, which would be the same thing as 75. That's a little messy. I'm going to put it down here, 75.65. And guys, we are so close to being done if we just put that guy in my square root. A lot of number crunching, a lot of playing with numbers, but hopefully in a way that's understandable. My final standard deviation ends up being, let's round to the nearest 10th, which would end up being 8.7. What does that mean? Well, 8.7 tells me basically how far, remember, standard deviation. What is the measure of typical value varies from the others. When we were looking at these ones, the 58, 75, 60, 48, the typical variance of one to another was about 8.7. So it is kind of in some sense an average. It's an average of what we call our squares of deviation. And that average, that mean, is the variance. So it's kind of like the average of these differences. technically the squares of those differences of how far off a data value is from the mean, from the X bar. So we averaged that, we square rooted, and we got our overall standard deviation, the typical difference or variation from one data point. So anyway, kiddos, I don't know if we're going to go ahead and go through and do another one just because there is so many numbers in this problem. There's a lot to keep track of. If we were to keep going in this specific problem, oh, I'm in the wrong one, we would go ahead and do the exact same thing for team B, and then we would kind of talk about interpreting our result. I'm going to go ahead and write down real quick our standard deviation for team A, because we just solved for that, and we got our standard deviation to be 8.7. But let's go ahead and check out the example in the book and see for theirs, and they did all the work for us as far as showing us the basic idea of what was going on. There we go. They were explaining in theirs the standard deviation for that cooking show and the ages of the kids on the cooking show, or the people on the cooking show, is about 4.2. And they said, okay, what that means is the typical age of a contestant differs from the mean by about 4.2 years. And for us, in our example with heights of the girls basketball team, on team A, the heights of each of these girls teams tends to differ by about 8.7. I think it was inches, if I remember right. I would need to come back here and look and see. Was it inches? Yeah, it was in inches. We could go ahead and look at, for instance, whenever we're doing statistical data, there are usually word problems that can kind of come up. We've already seen a few of them as far as what students are being paid in an amusement park, or the heights of girls on a basketball team, or the weights of a gorillas, maybe adult, maybe not. But we're not going to necessarily dig too much deeper in for right now, because I would rather you guys be able to get to your 11.1b homework. Now, 11.1b homework starts right here in number 17. Number 17, let me let you guys zoom in a little bit. Number 17 is giving us a table of data. And actually, if you guys notice, this right here literally just asks for us the range, which is so nice because range is so easy to find. Range just says who's the highest, who's the lowest of A, find that. Who's the highest, who's the lowest of B, find that, and compare the two. And compare the two. But then in the next problem, I'm almost positive they're going to have us start solving for something else. We are actually, there we go, doing numbers 19 and number 21. Then we skip, I think, to number 25 and do a couple others. But 19 and 21, oh, whew, 19 is really short, only 5 data points. They're having us do the range. Remember the range, the highest minus the lowest. That's it. The range, the highest minus the lowest. But then they're also having us do this standard deviation guy, in that they're also having us do this process with a table that you saw me do before. So guys, feel free to come back to this video anytime you want. You only need to watch it once for your homework, but you can definitely watch me do this example again, or walk through your example like number 19 for homework, or like number 21. Walk through the steps that I did, just with the different numbers. Just be careful that you recognize some of these different things that I was doing as far as why I was dividing by 10. Oh, because I divided by 10 2 different times. Because remember, there were 10 different data points. I had to divide by how many there were. So just kind of follow along with this example, and let's see how you do when you try to finish up 11A, 11B homework. Thanks for joining, guys. I'm going to go ahead and let you go and let you keep working on homework. All right, I'll see you later.